So this is our final lecture of the academic year. After this, we'll take a hiatus for the summer and then possibly regroup in the fall for September, depending on people's interests. So what I'd like to do today is to give a review lecture of the material that we've seen so far. And when I say a review lecture, what I don't have in mind is a sort of a summary of all the material that we've seen so far, because that's quite a lot of material. What I would like to do is to sort of cover the main ideas and the key examples into a more cohesive whole than what the presentation that we had when we're all learning together. So today we'll have the benefit of hindsight, knowing the significance of many of these constructions. All right, so in particular, I'd like to start out with some first definitions. So for example, the definition of a generalized complex structure, of course. Then I'd like to talk about the Courant bracket on the extended tangent bundle. And then finally, we will characterize, or we'll describe how generalized complex structures on smooth manifolds are complex Lie algebroids. And in fact, of course, as we saw earlier, there's more that can be said in terms of part 3, in terms of the complex Lie algebroids. We actually obtain a complex Lie bialgebroid or a sub-bialgebroid of the extended tangent bubble. But for today, I just want to focus on the basic ideas. Okay, so starting with section 1, first definitions. So our goal, or we might say that our at least formal goal here is to, or in generalized complex geometry, is to introduce a geometric theory, or a geometric field, theory that generalizes both complex and symplectic geometry. So in some sense, we want that geometric structure which is minimal, subject to the condition that it includes complex structures and it includes symplectic structures. So recall, by the way, that a complex structure is a endomorphism, or a section of the endomorphism bundle of the tangent bundle on M. So section such that I squared is equal to the negative identity on the tangent bundle, and including a integrability condition, which I'll just write integrability condition. On the other hand, a symplectic structure on a smooth manifold is a section, or is a two-form on M, which is closed in the sense that the exterior derivative of omega vanishes and is non-degenerate. in the sense that the interior product with omega. So this is the interior product with omega establishes a vector bundle isomorphism between the tangent bundle and the cotangent bundle. So this is not degeneracy. Our approach to achieve this goal is to identify both the complex structure and the symplectic structure. And so identify both I, the complex structure, and omega, the symplectic structure, with bracket orthogonal complex structure with let's see, with a bracket orthogonal complex structure on the fibers of the extended tangent bundle. So this is sort of like blackboard. I don't think it's blackboard bold T M, but it's T with two vertical lines, and this is defined to be the direct sum of the tangent space at x and the cotangent space at x. And then, as we'll see, we'll have an additional integrability condition. Okay, and then so an illustration of this. Let's see. I'll move. So in particular, we identify the complex structure. So at each fiber of the, or at each point of M, at each point x of M, we identify the complex structure I with a orthogonal, orthogonal complex structure J sub I on the fiber of the extended tangent bundle at x. Given by negative the complex structure on the tangent bundle, or on the tangent fiber, and the dual of the complex structure on the cotangent fiber. So an illustration. So then here's an illustration. We have the tangent fiber, the cotangent fiber. Their direct sum constitutes the fiber of the extended tangent bundle. So I guess this is the extended tangent fiber. On TXM, we act by negative I, and on TX star M, we act by I dual. So that's the complex side. For the symplectic side, we define our orthogonal linear complex structure on the extended tangent fiber at x to be as follows. So it sends tangent vectors to the cotangent fiber by contraction with the symplectic structure, and it sends cotangent vectors by the inverse map, or the negative inverse map, to the tangent bundle. And note that this note that this inverse map exists because omega is non-degenerate. And so the illustration here is that so omega is mapping us from the tangent fiber to the cotangent fiber. And negative omega inverse takes us back. So in particular, let's say here is a tangent vector x. So tangent vector capital X, then j omega of x is equal to the interior product of x with omega. And then note that there's a sort of a characteristic difference here, where in the case of when we start with an actual complex structure on M, the induced generalized complex structure is preserving the tangent and the cotangent fibers. In the symplectic case, the generalized complex structure is actually completely interchanging the tangent and cotangent fibers. So this is actually, so in some sense, the genuinely complex case and the symplectic case are at two ends of the spectrum, and the spectrum goes by the name of type. Yes?
So, and if, can we add the two matrices? And for example, one half of the sum is...
Can we average them? No. Because I could take I, and I could take negative I, and then their sum is going to be 0, and that's not a complex structure. Do you see? Like, I could start, so we could take this arbitrary complex structure on M, capital I, and then, well, its negative is also a complex structure on M. The induced generalized complex structures are going to be minus I star and I minus I star, and their sum is going to be 0.
But can you add the two?
These two here. These specific ones?
For example, or?
I don't know. But it doesn't form a vector space in general. Like we can't just add any two generalized complex structures and get another generalized complex structure.
I see. Okay.
And then there are intermediate cases between the complex case and the symplectic case, and that's that's characterized in terms of the notion of type, which roughly tells us how to what extent the generalized complex structure will have the cotangent fiber overlap with itself after we act by the generalized complex structure. Okay. So I said, I should explain this term. I said brackets orthogonal complex structure on the extended tangent bundle. So this these brackets refer to the canonical bilinear pairing on the fibers of the extended tangent bundle, and it's given as follows. So x plus alpha paired with y plus beta is equal to 1/2 alpha evaluated at y plus beta evaluated at x. So this is for, so these are elements of the extended tangent fiber at x. That is, x is a tangent vector, and alpha is a covector. And then there's an equivalent, and so as we saw in the first lecture, there's an equivalent characterization of such a orthogonal complex structure, or orthogonal linear complex structure, and is given as follows. So, we have a 1-1 correspondence between orthogonal linear complex structures on the extended tangent fiber, the extended tangent space at x, and maximal isotropic splittings of that of the extended tangent fiber with the extended tangent space at x into a so this is a decomposition, a direct sum of the extended tangent space at x into a maximal isotropic subspace L and its conjugate L bar. And then, so for these key examples, recall that we had so the standard example for the complex case then is that this maximal isotropic subspace L is given by the direct sum of the holomorphic tangent fiber at x. I'm sorry, the anti-holomorphic tangent fiber at x. So the direct sum of that with the holomorphic cotangent fiber at x. So that is L equals the direct sum of Tx 0, 1, m with Tx star 1, 0, m. In the symplectic case, it's not as straightforward to draw it like this because the space doesn't the space L doesn't split in this way.
So
Yeah.
these are the complexified.
Yes, this is
Okay.
yeah, thank you. Here we go. And so this is so in the symplectic case. So here is the complexified cotangent bundle, or cotangent fiber at cotangent space at x, the complexified tangent space at x, and then L is the graph of negative I omega, where again we're thinking of omega as a map from the tangent bundle to the cotangent bundle. So for the people who have arrived recently, I'll state that so today is it's the final lecture of the academic year, and so what we're doing is this is just a review of the main ideas of the lecture series so far. And not a summary of everything that we've done, just covering the main ideas. And I apologize, it's extremely hot. I didn't realize it gets this hot in St. Petersburg. Okay, so now we give the definition of a generalized complex structure on M. Using these, so we're taking from these ideas to give our general definition, which is a generalized complex structure on M is a smooth assignment of orthogonal, or specific bracket orthogonal, linear complex structures on the fibers of the extended tangent bundle such that the plus I eigenbundle L in the complexification of the extended tangent bundle of J is Courant integrable. And so, okay, so now all that remains to be defined is what we mean by Courant integrable, and this is the content of the next section. So that brings us to part 2, the Courant bracket. So our aim, or our goal, let's say goal again. Our goal now is to extend the Lie bracket on the tangent bundle to the extended tangent bundle. So extend the Lie bracket brackets on Tm to T2 lines M. That is the direct sum of the tangent bundle and the cotangent bundle. And the definition turns out to be as follows. So the Courant bracket on the extended tangent bundle is given by so x plus alpha, y plus beta. X and y are elements of the sections of the tangent bundle. Alpha and beta are sections of the cotangent bundle. So their sums live in the space of sections of the extended tangent bundle. Okay, so then the definition of the Courant bracket, and so again we use these double vertical line brackets. The definition is given by, well, first of all, on the vector field component, we just take the ordinary Lie bracket of vector fields. So this is a section of the tangent bundle, and then we have the rest. So we have this other side, which is a section of the cotangent bundle. And I guess I'll read out what the definition is. So okay, so it's the Lie bracket of x and y plus the Lie derivative in the direction of x of beta minus the Lie derivative along y of alpha minus 1/2 the exterior derivative of the interior product of beta with x, the exterior derivative of the difference between the interior product of beta with x and the interior product of alpha with y. And then there are some observations about this. So I'm going to move this there. So properties. First, observe that as required, only one, the Courant bracket of x and y is just the Lie bracket of x and y. Second, note that the Courant bracket of alpha and beta vanishes. We plug in, if x and y are both 0, then this right-hand side will be 0. And then two technical conditions that we'll use in the next section. So 3. Namely, we'll see here that the Courant bracket does not, or we'll recall from the previous lectures, that the Courant bracket does not form a Lie bracket on the space of sections of the extended tangent bundle, but we can still characterize the extent to which it does not. So the Jacobiator of sections A, B, and C of the extended tangent bundle, maybe I'll indicate what these are, is 1/3 of the exterior derivative of the sum, or of this following expression. Or I'll just say cyclic permutations. Cyclic permutations. And so here, A, B, and C are sections of the extended tangent bundle. And lastly, so fourth, we'll see that then even if the Jacobiator did vanish, even if we happened to be in such a case where that occurred, the extended tangent bundle still wouldn't form a Lie algebroid over M because it doesn't satisfy the Leibniz condition, as we'll now indicate. So the Courant bracket applied to, on the left-hand side, a section A, and on the right-hand side, a smooth function f, scaling b, is equal to f multiplied by the Courant bracket of A and B plus pi. So here pi is the projection from the extended tangent bundle to the actual tangent bundle. So pi a. This is a vector field. And here we're applying it to f, so we're taking a derivative of f along pi a, or in other words, along the vector field component of a. And then we're multiplying that by b. And if this were the equality, then we would satisfy a Leibniz condition. So this is the Leibniz equality. But we don't. We have an extra term, a negative pairing of A and B, scale, and then that scaling the exterior derivative of f. Okay, so note that in both of these cases, the failure to be a Lie algebroid or for the Courant bracket to be itself, or a simpler condition for the Courant bracket to be a Lie bracket, has to do with the canonical pairing on the extended tangent bundle.
The differential is not applied to the pairing between A and B as well?
I don't think so. Not in my notes. Should it be?
My intuition would make it because yeah.
Yeah, I can check it and then I can post on the Telegram chat. So maybe I'll put a small first word there. Okay. So what? Okay, and then I'd like to address the question of why this is a natural choice of generalization, like why the Courant bracket is a natural definition. So I'm going to, let's take a really short break. I'll erase the boards and then we'll do that. So. Oh yeah, you have it.
No, but because it seems the
Okay, I think it's right. All right, so now the question is, why is the Courant bracket, or how is the Courant bracket a natural choice of generalization of the Lie bracket? And so for our answer, we'll recall that, so an elementary geometry computation shows that the interior product with the Lie bracket of x and y and some section or element of the exterior algebra bundle is equal to, so this is going to be the exterior derivative of the interior product with x, of the interior product with y of rho, or with rho, plus the interior product with x of di, the interior product with y rho, minus iy d ix rho, minus iy ix d rho. Well, so this is for, again, vector fields x and y, and any differential form rho. Vector fields are, in particular, sections of the extended tangent bundle, in terms of the extended tangent bundle and the Courant bracket, this bracket here is the Courant bracket, and the interior product with these sections of now what we're considering to be a subbundle of the extended tangent bundle. This is just the canonical Clifford multiplication of with sections of the generating vector space for the I'll write it out. Okay, so this is the Courant bracket of x and y, Clifford multiplication on, and then Clifford multiplication on rho. Recall that the exterior algebra bundle on M, the exterior algebra bundle of the dual tangent of the cotangent bundle on M is the space of spinors for the Clifford algebra generated or associated to the extended tangent bundle with its canonical bilinear symplectic. I'm sorry, canonical bilinear form. So this is d let's see, x dot y dot root plus x dot d y dot rho where again this we have a Clifford multiplication from the Clifford algebra generated by the extended tangent bundle and its canonical symmetric bilinear form on the space of, or the spinor bundle, which in this case is the is the exterior algebra bundle of the cotangent bundle on M, and it's given by x plus alpha dot rho is defined to be the interior product with x, with respect to x of rho, plus the wedge of alpha and rho. So here we only have vectors. We don't have any cotangent components. So it's just the interior product, and that's how we move from this first equality to the second equality. And now we just we extend this formula. We say, okay, well we want this formula here to characterize the Courant bracket. So instead of it being satisfied on just the tangent subbundle of the extended tangent bundle, we're going to assert that it be satisfied on the entire, on sections of the entire extended tangent bundle. And so we just get, we just replace the vector field X with the extended, I don't know, we could call it extended vector field maybe, A, and we replace Y with the section of the extended tangent bundle B. So this is and then it turns out that this works. That not only does this give us, does any kind of bracket satisfy this, but this uniquely determines the Courant bracket. This expression. And then note that we can extend, and we do extend. So we can extend the Courant bracket on the extended tangent bundle to the complexified extended tangent bundle by linearity. And now, so now we're at the final section, section 3. We're making good time. So generalized complex structures so generalized complex structures as complex Lie algebras. So let J be a generalized complex structure on M. And then let L be the plus I eigenbundle of J. So note that L is a subbundle of the complexified extended tangent bundle. So L is first, Courant integrable by definition. So this means that for all sections A and B of the extended tangent bundle, we have that their Courant bracket, the Courant bracket, oh, I'm sorry, these are sections of L. The Courant bracket is, again, a section of L. And L is maximal isotropic, so in particular it is isotropic, which means that for all A and B, all sections A and B of L, the pairing between A and B vanishes. And so now we'll apply these two facts to to properties 3 and 4 of the Courant bracket. So these two properties describe how the extended tangent bundle fails to be a Lie algebroid. So we have I'll call it A. The Jacobiator of A, B, C is equal to 1/3 the exterior derivative of the same expression as before. And because L is Courant integrable, for all, let's see, so for all sections A, B, and C of L, we have that, well, the bracket of A and B lies, or is again a section of L, which means that since L is isotropic, this the pairing between the bracket of A and B and C vanishes. So this vanishes, but then this entire right-hand side vanishes. So this is 0. So we've just shown that the Jacobiator is 0, which means that the restriction of the Courant bracket to sections of the to sections of L is a Lie bracket. And then secondly, B. So the next, so and this is part 4 down there. We have the Courant bracket of A and FB is equal to F scaling the Courant bracket of A and B plus the tangent component of A applied to F, and that scaling B, and then plus the canonical pairing of A and B scaling the exterior derivative of F. But again, since L is isotropic, this canonical pairing vanishes. And so we're left with the Leibniz condition. And so the upshot is that, therefore, and of course this is we're sort of covering things that we've seen before, and so we're going quickly over, we're leaving out a whole bunch of the other conditions that pertain to some of these things. But therefore, L, the plus A eigenbundle, with the Courant bracket restricted to sections of L, and the projection to the tangent bundle, or the in this case the complexified tangent bundle, is a complex Lie subalgebroid of the complexified extended tangent bundle. And so now we'll just recall the definition of a complex Lie algebroid.
But I thought that the complexified tangent bundle is not a Lie algebra.
The complexified tangent bundle?
Is it? It is a Courant algebra, but not a Lie algebra.
The extended tangent bundle?
Yes.
The extended tangent bundle is not a Lie algebroid, or a complex Lie algebroid.
Okay.
But L is the sub. It's sort of like you can have a subgroup of a semigroup.
Okay.
I mean, maybe I'm using this improperly. I'm saying it's a substructure, and it is a. Yeah.
Okay.
Okay. So definition: a complex Lie algebroid E brackets, let's see, brackets A comprises one, so three data. First, a complex vector bundle E over M. Second, a Lie bracket say brackets E on the space of sections of E over M. And thirdly, an anchor map A from E to the complexified tangent bundle. This is a complex Lie algebroid. Such that the following conditions hold. First, the anchor map induces a Lie algebra homomorphism on the space of from the space of sections of E to the space of sections of the complexified tangent bundle. That is, A applied to the E bracket of X and Y is equal to the standard Lie bracket on TMC of the anchor map applied to X and the anchor map applied to Y. So this is for all, such that for all x, y, so sections of E and F, smooth functions on M. So the second condition, that we have the Leibniz rule. It's the Leibniz condition. And so, to me, this Leibniz condition sort of says that these elements, x and y, kind of are vector fields. They're like sort of like generalized vector fields in some sense, it seems. And then thinking about the definition of Lie algebroids a bit more recently, it seems that maybe they can be thought of as like generalized or inverse foliations. If we think of a foliation on M, or let's say a foliation as an integrable distribution. Yeah, they're more like generalized integrable distributions. If an integrable distribution is like a thinning, or it's an integrable thinning of the tangent bundle, which means that we're removing degrees of freedom, or we're removing directions from consideration, then it seems that a Lie algebroid is kind of like, it allows us to thicken certain directions. So it's like a lumping of the tangent bundle, where we can not only restrict or remove certain directions, but we can also duplicate the dimensionality of certain directions. So we can have, say, 2 dimensions in the Lie algebroid, which correspond to 1 direction along M. So just like a foliation, but going in the opposite direction as well. All right, so this is everything for today. Are there any questions? Yes.
Yes. So we see that. So maybe there is a statement like generalized complex structure correspond to a Lagrangian Lie subalgebroid of the extended tangent bundle.
By Lagrangian, you mean maximal isotropic?
Yeah, like half-dimensional.
I don't think so. Because it has to. It's not enough just to have the maximal isotropic condition. It needs to split the extended tangent, the complexified extended tangent bundle fiber-wise, with its complex conjugate. So I think it is the case that if you said but then we're basically just getting the original definition. So it's a fiber-wise maximal isotropic splitting of the extended tangent bundle.
Because I'm thinking about, so I heard about Dirac structures, which are maximally isotropic sub-bundles.
Yeah, so that's where this came from. That's, I think, where the Karat bracket came from. I think the same thing, we were at some point much earlier in this series, I think I was going to mention, or we didn't have time, that another way of thinking about generalized complex structures, or about these plus I eigenbundles, is as complex Dirac structures. But yeah, in the real setting, yeah, we can remove all this complexification stuff, and I think the Dirac structure then gives us a Lie subalgebroid of the extended tangent bundle. Any other questions? Well, if there are no other questions, then I hope to see people in the fall.
Yeah, perfect. So do you plan to continue this seminar?
Yeah, I'd like to.